Hello, this is Mr. Josephs, and today I'm going to read the discussion part of the Lab 10, Polarity of Covalent Bonds and Molecules. So let's get started. So one result from a Google search for the definition of polarity results with the state of having two opposite or contradictory tendencies, opinions, or aspects. In chemistry, this means that there is a difference in the electrical charge from one end of something to its other end. This something might be an entire molecule or a singular bond within a molecule. The Lewis electron diagram below illustrates the difference between a whole water molecule and a bond within that water molecule. So you can see the bond within the water molecule. You have the shared electrons, and then you have the water molecule as a whole. And it's important to be able to distinguish between a bond in a molecule and a molecule. Now that we have established that either an entire molecule or a single bond within a molecule can be polar, let's explore what properties might determine polarity. So the property that determines the polarity of a bond is similar but slightly different than the property that determines the polarity of an entire molecule. So scientists measure electronegativity as a value of how strong a nucleus of an atom pulls on bonded electrons. The greater the electronegativity value of an atom of an element, the greater it pulls on the bonded electrons. So therefore, when two atoms form a chemical bond, we can understand that the behavior of the bonded electrons, based on electronegativity values. So let's see what that means. So right here, in diatomic elements, the 7 elements that form molecules of pairs of atoms form pure covalent bonds. This means that the electrons are shared equally between the atoms in the bond. An example is diatomic chlorine shown below. So let's look at this. So we can see that we have a chlorine atom covalently bonded to another chlorine atom, and they are sharing these electrons in between completely equally because their electronegativity values are exactly the same. Chlorine's electronegativity value has to be equal to the electronegativity value of another chlorine atom. Okay, so it makes sense that the chlorine atoms share their bonded electrons equally because they each have the same nuclear charge, the number of protons, and pull on electrons equally. This bond is called a nonpolar covalent or a pure covalent bond. And this is because there is absolutely no difference in charge from one end of the bond to the other. Remember, the Google definition of polarity requires there to be a difference or an opposite in something. There is no difference in charge from one side of the chlorine bond because of the equally shared electrons. So there's no negative end or net positive side. However, the electrons in the bond between an atom of hydrogen and an atom of chlorine are not shared equally. The bonded electrons are pulled closer to the atom of chlorine than they are to the atom of hydrogen. How can we know this? This is because we can look up the electronegativity values of both atoms in reference table S. We note that the electronegativity value of chlorine is higher than the electronegativity value of hydrogen. This electronegativity difference indicates that chlorine will pull those bonded electrons closer to itself because it has a higher electronegativity value. We are lucky to easily know the behavior of bonded electrons because scientists have done the hard work of measuring the pull of electrons in bonds and assigning electronegativity values to the elements as a result. Because the electrons are not shared equally between a covalently bonded hydrogen and chlorine atom, it is considered a covalent polar bond. One end of the bond has a slightly positive charge and the other end a slightly negative charge. The Google definition of polarity applies. To show the direction in which the bonded electrons are pulled within a polar covalent bond, an arrow is drawn pointing from the atom with the lower electronegativity value toward the atom with the larger electronegativity value. The tail of the arrow is crossed with a small line to make a sort of plus sign, and you can see it in the image below. there's a plus sign on this arrow, and the arrow points this way. Because electrons are pulled more toward one atom, the region around that atom becomes slightly negative. However, an electron isn't entirely transferred as it is during the formation of an ionic bond. So as a result, we say a partial charge is created. A partial negative charge is shown using the lowercase Greek delta letter. This is a Greek delta letter right here. And using it with a superscript negative sign. While a partial positive charge is designated with the same Greek letter, but with a superscript positive sign. The polar bond between an atom of hydrogen and the atom of chlorine is shown in the image below, with both the direction in which the bonded electrons are pulled along with the partial charges around each atom. And you can see that, remember, this being an more electronegative, the chlorine is pulling those shared electrons toward it and causing a partial negative charge on this end of the bond. Well, a partial positive charge is on this end. These bonded electrons are not shared equally, and then this symbol is showing the positive or the negative partial charge. Okay? This arrow is basically showing which direction the electrons will be going. And that's a polar covalent bond because one side has something different than the other side. And in this case, the something different is charge. All right. So the difference between atoms forming a covalent bond do not have to have the exact same electronegativity value for that bond to be considered as nonpolar. So what do I mean by that? Small differences in electronegativity may exist and the bond is still considered nonpolar. So you can have a slight electronegativity difference and you would still consider it nonpolar. The electrons don't shift over enough to be considered, make that bond considered polar. So see the table below that classifies bonds based on electronegativity differences between the atoms that forming that bond. So we take the difference between the two and we can see that. So the difference between these two is going to be greater than 0.4, but it's going to be less than 1.7, and it's going to be considered a polar covalent bond. Okay, as can be seen from the table, a bond might be considered nonpolar even though the electronegativity difference between the bonded atoms is as much as 0.4. The polarity of the bond increases as the electronegativity difference increases. Eventually, the difference in electronegativity is such that the electrons can no longer be thought of as even being shared, but rather transferred from one atom to the other. This, of course, is the definition of an ionic bond, right? It may surprise you to learn that all bonds simultaneously have both covalent and ionic nature. They both share and they transfer electrons. The extent of the ionic character of a bond is tabulated in the table entitled Relationship Between Electronegativity Difference and Ionic Character. That's farther on in this lab. Right here. Okay, now that we have discussed the property used to determine bond polarity, electronegativity difference, let's turn our attention to determining the polarity of an entire molecule. That is, how do we determine if one end of a molecule has a positive charge and the other end a negative charge, or a slight positive charge or slight negative charge? If a molecule has only two atoms and the bond between those two atoms is polar, then the molecule itself is polar. We've already provided an example of this with the molecule of hydrogen chloride, HCl. This is a molecule, and there's only one bond in it, and it's a polar bond, and so the whole molecule is also polar. So this is an example of a polar molecule with a polar bond. In the image below, notice the Lewis dot diagram of a molecule of NH3 shows that it is polar. One side of the molecule is partially negative, right here, while the other side is partially positive. Right, so that's a polar molecule. But why? Why do we say that's a polar molecule? How can we tell? Now let's consider a molecule of CCl4. CCl4, so carbon tetrachloride. Every bond within this molecule is polar because the electronegativity difference between the carbon atom and a chlorine atom is 0.6, which is greater than 0.4, so we've got a polar bond. This bond is polar right here. This bond is polar right here. However, this whole molecule does not have one end that's partially positive and one end that's partially negative. This means this molecule is not polar. It's nonpolar. So see the Lewis dot diagram below shows that the distribution of electrons around the molecule, the distribution of electrons is even all the way throughout this molecule. So even though it has polar bonds, the molecule itself is not polar because it doesn't have a positive and negative end. Okay, now we can see that the charge distribution evenly throughout the molecule, so no polarity is developed. No side of the molecule is positive and the other side negative. This is true even though all the bonds within that molecule are polar. So what are the differences between the molecule of NH3 and the molecule of CCl4 that make one polar and the other nonpolar? It all comes down to shape. So this is a polar molecule with polar bonds in it. This is a nonpolar molecule with polar bonds in it. Nonpolar molecules must demonstrate symmetry both vertically and horizontally. Polar molecules, while they must contain polar bonds, cannot be symmetrical about at least one axis. Note the lines of symmetry on the molecule of NH3 compared to the molecule of CCl4 in the images below. So here's the same molecules we saw before, and we're going to look at them. Their symmetry about the vertical axis. H3N or NH3 is symmetrical about the vertical axis, but it is not symmetrical about the horizontal axis. Whereas CCl4 is vertical about the vertical axis, or symmetrical about the vertical axis, and symmetrical about the horizontal axis. So that is the difference. We need to have symmetry both around the horizontal axis and the vertical axis, and that will make a molecule nonpolar. So note that the molecule of NH3 does not show symmetry about both axes, while the molecule of CCl4 does. This means that the molecule of NH3 is polar, while the molecule of CCl4 is not. A molecule is therefore polar if it contains polar bonds and is not symmetrical about the vertical and horizontal axes. Lewis dot diagrams can sometimes be limiting since they show the compounds in 2 dimensions, while actual molecules exist in a 3-dimensional world. So colored wooden or plastic ball models can thus be used to represent atoms. These balls have holes drilled in them at the location of unpaired electrons where covalent bonds can potentially form. Sticks and springs are used to represent bonds. Single bonds are represented with sticks, while double and triple bonds are represented with 2 or 3 springs. And that's what you can use during this lab. And you will see how symmetry will determine if a molecule is polar or nonpolar, and you'll look at electronegativity values to see if a bond is polar or nonpolar. I hope you learned something today. That's all I got for you today.